Now we have the last question from the 2025 paper, which is a nice question on rates. Some of this question's pretty straightforward, but only really if you've studied rates in class before. If you haven't studied rates, some of it's probably going to seem quite unusual. So we've got all the usual information here about the reaction, which is quite important. It's also this enolization reaction is quite a nice reaction, or equilibrium. If you're not sure, this is called an enol. The ene is for the double bond here, and the ol is for the alcohol here. So this equilibrium between a ketone and an enol is something that's probably worth knowing. And then we have the rate information. All right, so just to bear in mind that step 1 is the forward reaction from A to B. Step 2 is the reverse reaction from B to A. So information about the equilibrium is going to be given to us by the difference between these two, or the ratio of those two. And then this is the important part here. So any species involved in or before the rate determining step could affect the overall rate and therefore appear in the rate equation. And then it says at high concentrations of I2, the rate determining step is step 1. So in question A, it says which of the following species will be included in the rate equation for the formation of C at high concentrations of I2. So just as we've had up here, we're told that this is the rate determining step at high concentrations of I2. So A is the only thing that appears in that rate equation. You may be tempted to look here at C, okay, and you think, well, A formed B, and then B and I2 together form C, and I2 is here in the rate equation. So why isn't that affected? And it's because we're told that this is the rate determining step. So this step is very, very fast, as you can see from the very high rate constant. So even though we have I2 in this rate equation, because this is the rate determining step, we only consider A. So we go ahead and I'm going to choose A for that. Okay, so moving on to the next part of the question, we're given this graph. The initial rate of formation of C was measured at different concentrations of A and plotted on a graph. Using the graph or otherwise, write the rate equation for the initial rate of formation of C at high concentrations of I2 again. So it's that same condition, high concentrations of I2, in terms of the concentrations of A and I2 and an appropriate combination of the rate constants. Well, this is deceptively simple because we've just, in the previous question, said that the only thing that affects the rate of formation of C at high concentrations of I2 is A, coming from this rate equation here. So the answer is simply just that the rate is that K1A. Now, the graph we can use in this part of the question if we really needed to, but it's going to be more useful in the next part of the question. You should be able to see from this graph, as it's a concentration against rate graph, which is linear, that it is going to be a first order reaction. In other words, if I have the relationship rate equals Ka, I know that if I double the concentration of A, I will double the rate. And you can sort of see that here. If I go to 4, if concentration is 4, I get 175 here. Be careful to read this scale properly. It's 100, 125, 150, 175, 200. So if I double the concentration from 4 to 8, I should get double 175, which is 350, which is what I get. So it's a first order reaction quite clearly. So we can then go on to part 2, determine the value of the rate constant K1 with appropriate units. Well, quite obviously, the rate constant K1 is going to be equal to the rate divided by the concentration, or in other words, it's going to be equal to the gradient of this graph here. So up to you, you can work out the gradient however you want. I'm going to go ahead and use the values that I just mentioned. So that's going to be the difference between 350 and 175, which I doubled, so it's obviously just 175, and 8 minus 4. Okay, and if I do that on my calculator, I just get 175 divided by 4, which is 43.75. However, most importantly, this is micromole. All right, so I'm going to put my rate into, well, if this is moles per decimeter cubed, I can't really have this as micromoles per decimeter cubed, so it's essentially I need to times this by 10 to the minus 6 to account for the micromole in the, or the micro factor. So if I divide it by a million, I get that, which is 4.38 times 10 to the power of 1, 2, 3, 4, 5. Minus 5. Okay. Oops. Okay, so far so straightforward. So now we move on to low concentrations of I2. So at low concentrations of I2, the rate determining step is now step 3. Alright, so it was initially at high concentrations that this is the rate determining step, the keto to enol, but at low concentrations it's now the addition of the iodine to the enol, which is going to determine our rate. Under these conditions, the ketone and enol forms exist in an equilibrium. So understanding this statement here is key to understanding the rest of the question. All right, so I'm just going to spend a little bit of time explaining what they're talking about. If we have high iodine concentrations, then step 3 is the, step 1 is the rate determining step, okay? Because at this step 3 here is really, really fast. So step 1 is a little bit slow, so this turns into this quite slowly, but then once this is formed, it immediately forms this. All right, so this is very, very fast, which means that if I have enough I2, as soon as any of this appears, it reacts with the I2 to make this. So the I2 is basically just waiting around for this to form, which means that the K1, that's our slow step, right? Well, not our slow step, our rate determining step. However, if I have a low amount of I2, all right, then once this forms, there's none of this readily available to react, which means that this can go back into this can go back to this can go back to this, all right? So therefore, this equilibrium has time to establish, all right? High concentrations of this gets removed immediately, the equilibrium can't establish. Low concentrations of this has time to go backwards and forwards, and the equilibrium gets formed, all right? So it says now the equilibrium between A and B can be described using the equilibrium constant KEQ. Write an expression for B at equilibrium in terms of A, K1 and K2. Now, if you've studied rates in class, this relationship between the equilibrium constant and rate constants is something that you should have covered. It's going to be fairly simple because the equilibrium constant, obviously, for the reaction between A and B is just going to be the concentration of B over the concentration of A. And then we equate that to well, essentially we just plug that into there. And so then our equilibrium, or our expression for the concentration of B, is just going to be K1 over K2 multiplied by the concentration of A. Okay, then D. Using your answer for part C or otherwise, write an expression for the rate formation of C in terms of the concentrations of A and I2 and the combination of the rate constants. Okay, well, that's also fairly straightforward because I'm told here that the rate of formation of C is, so I have rate equals K3BI2 and then all I need to do is just take my concentration of B and put it in here. So that then becomes K3, K1 over K2, A, I2. So it looks a bit messy, but you know it makes some sense that we're going to have our rate is going to depend on the concentration of our ketone and the iodine, and then it's going to be the rate constants for the forward reactions and the rate constant for the reverse reaction all in there. Okay, so at intermediate concentrations. Okay, intermediate concentrations. Step 2 and step 3 occur at similar rates. All right, so obviously now that we got a sort of intermediate amount of this, step 1 and step 2, that's going backwards and forwards. Therefore, we cannot assume that the ketone and ethyl forms are in equilibrium. Sorry, I think I misspoke then. So if step 2 and step 3, so step 2, the backward reaction, and step 3, the forward reaction here. So this is forming, but the rate of it turning back into the ketone and the rate of it reacting to form this are equal, so it doesn't really give it time for the equilibrium to establish. Therefore, we cannot assume that the ketone and ethyl forms are in equilibrium. Under these conditions, the concentration of B can be written as this. Write the formation of C at intermediate concentrations of I2 in terms of the concentrations of A and I2. So this is the same as question D. However, we're now given this as our expression for the concentration of B rather than the one that we were using before that we'd worked out in part C. So it just becomes, we're going to say that our rate for the formation of C is K3BI2 again, as we had before, but now we're going to put this value of concentration of B into here. So that's going to become, so I'm going to put it in K3, I2, write it like that, and then I'm going to write K1A over K2 plus K3 I2. So you can tidy it up if you want, put the rate constants next to each other and the concentrations next to each other. That's fine, but there's no way of simplifying that, so we're going to leave it there. Okay, I think up until this point the question is, if you are familiar with rates, fairly straightforward. It's just plugging numbers into or plugging expressions into other equations. Then it gets a little bit tricky with this. Compound A, so our original ketone, can form two different enols. So this is the one that we have been looking at. All right. Then it can also do this enolization on the other side. All right. And then we're given rate constant values for K4, K5, K6. What I'm going to do is I'm going to write in all of the rate constant values, because at the moment I've got lots of different information. I know I've got values for K1, K2, K3, K4, K5, K6, but I'd like to have it all on the diagram itself. So I'm just going to write those in. So there are the values, and now we're ready to go on and answer question F. So we have to choose between C and E for which statement is true for which one. So product whose reaction pathway has a larger rate constant for the first step. So C or E? Well, for the first step, for C, the rate constant is 4.4 times 10 to the minus 5. For E, it's 2.9 times 10 to the minus 6. So C is the correct answer. Is the major product at high I2? So remember, if we've got a lot of iodine, as soon as this forms, then it will react immediately. And we can see that for C, this reaction pathway, because the rate constant for the first step is larger, this rate constant here is larger than this one, it means that this enol is forming faster than this enol. So therefore, as soon as this forms, it will react with the I2 and go to this. All right? This will form slower, so it won't be able to do this reaction as fast. So at high iodine, we prefer this reaction pathway. This reaction pathway might still happen, but the formation of this enol is slower. So as soon as this one forms, it reacts. The product whose reaction pathway has a larger KEQ. So for this one, you can go ahead and you can do the maths here. So if I take the ratio of those two, 4.4 to the minus 5 divided by 8.3 is going to give me, I haven't got my calculator set up like that. That's not right. 5.3 times 10 to the minus 1, 2, 3, 4, 5, 6, minus 6. Whereas this one is going to be 2.9 exponential minus 6. Divided by 2.1, that's the minus 2, going to give me 1.3. Okay, so you can see quite clearly that for this reaction pathway, the equilibrium constant is going to be larger. All right. So now, what happens at low iodine concentrations? So at low iodine concentrations, where there isn't a lot of this available to react with the enol, there isn't a lot of this available to react with the enol, then whichever one of these exists in a larger quantity at equilibrium. Because remember, when there's not much iodine, this isn't reacting straight away, which allows the equilibrium time to establish. So if I've got low iodine concentrations, this equilibrium is able to establish, this equilibrium is able to establish, but once they're established, the equilibrium constant for this one is larger, so I'll have more of this. So this is more likely to react with my iodine. So it's a nice question because this reaction is favoured when there's lots of iodine because this reaction happens fast. This reaction is favoured when there's not much iodine because this one allows the equilibrium to establish and this to have a larger concentration. All right, so it's easy to do the question up until this point without thinking too much about the reaction, but if you think carefully about the reaction, there is some very nice chemistry happening. All right, so calculate the concentration of, this is the last part I think, calculate the concentration of I2 required to form the products C and E at the same rate. All right, so we know that this one is favoured by high concentration, this one is favoured by low concentration. The question is, what is the sort of the intermediate iodine concentration that allows them both to be formed at the same rate? And very nicely, they do give us a hint. You will need to use an expression for the rate at intermediate concentrations of I2. Well, luckily, we have that expression because it is the answer to part E, where we were asked, write the rate of formation of C at intermediate concentrations of I2 in terms of the concentrations of A and I2. So that is our expression, all right? Now, this is going to get a little bit complicated, although it doesn't really need to be. So this is our rate of formation of C. So I'm going to write it out just carefully. So for C, our rate is going to be K1, K3, I2, A, over K2 plus K3, I2. All right, now I can write the same thing, but for E. Okay, so it's just going to be the same thing. But now, instead of K1, K2, K3, I've got K4, K5, K6. So K1 I'm going to replace with K4. K3 gets replaced with K6. Then I have my I2 and my A. And then K2 is now K5. And K3 again is K6. So this is the rate of formation of C at intermediate iodine concentrations. This is the rate of formation of E at intermediate iodine concentrations. And it asks us when is the rate of formation of C equal to the rate of formation of E. In other words, when do these two equal each other? So set them equal to each other, then we can cancel the I2 and cancel the A, and then we need to find an expression for the concentration of iodine. So we're going to have to do a little bit of rearranging. Then I'm going to expand the brackets. Then I'm going to collect my like terms so I can factorize out the iodine concentration. So hopefully at this point you can see what the general idea is. You do need to be very careful as you go through that you are copying these subscripts for the 1, 2, 3, 4, 5, 6 very carefully. You don't want to get them mixed up. So at this point now you can just factorize out the iodine and divide by the factored term, and then you just put all of the rate constants in. It's a bit of work on your calculator, but you you should get the answer for the iodine concentration, which is 1.11 times 10 to the minus 6. I'm not going to do the whole thing on my calculator. All right, and that's the end.